Hi, and good morning, good afternoon, good evening, whatever you are. So, welcome back to another video related to turbulence models in OpenFOAM. This time, still working now with the flat plate, the quintessential validation case, let's say in CFD for turbulence modeling. And this time, let's move to the Spalart-Allmaras model. Okay, fantastic model. I love it. I don't love it more than the K Omega 2006, but it's a very good one and I use it very often. It is a one equation model, so we're going to get out of that bubble of two equation models where we have two variables that we can use to compute viscosity, integral length scales, and so on. So this is very different. It is a very synthetic model. Okay, so we're going to go through the theory a little bit, and to mention that this is a low rate, high rate model, specifically formulated for turbomachinery aerospace application, but it is very general. You can use it for any application, but the origins of this model is this aerospace applications. And in OpenFOAM, it tends to work better for low rate, but you can use it for high rate. So we're going to go through the implementations on theory and then work in the cases for low rate, high rate, and we're going to look at boundary conditions and some other details. So now let's move to the theory. Okay, as usual, I always like to reference to this website, the Turbulence Modeling Resource, from NASA. These guys, they know 2 or 3 things about CFD. So previously we covered the K Omega family model, these two. Now let's move here to one equation. And look that there is not only one, there are different models, but probably the most popular one, it is the Spalart-Allmaras. So if you click here, you're going to get into the theory, many models, many implementations. I think of all the family of turbulence models, this is the one that has been modified the most. Okay, there are many modifications, many corrections, something that probably you're aware that turbulence models, they are not perfect. So you do an initial implementation, then you realize that it's missing something and you add a correction. So this one has many corrections. Okay, so you see this is the longest web page in turbulence here in this website. But basically, let's stick with the standard Spalart-Allmaras. So this is the formulation, the equation. So look at that always, as I mentioned, they take the general form of the transport equation. Okay, you have a production, destruction, transport, and then some correction methods. Something very important, don't think that you write down this equation like, okay, this is a transport equation, put these terms, and that's all. Behind that, there is some reasoning, okay, there is some logic, so there is some mathematics and some experiments just to calibrate coefficients, get blending functions, and so on. Okay, so in this model, we introduce the modified viscosity to compute the turbulent viscosity. Okay, so this modified viscosity, it has the same units, and our goal is just to get that. So look at that turbulent viscosity, compare it like this. You have then this blended function that will do its job. Then look at that, this model is also introducing in some way vorticity. Okay, you have this quantity here, okay, the vorticity tensor, then you have many more functions. You have then, as I mentioned, it's very important to read limitations and implementation of the model, what is recommended by the author, or in this case by this website. So here, nu tilde at the wall 0, nu at the wall is also 0, and then far field values, something from 3 to 5, the molecular viscosity. I tend to do 1 to 10, but there are different corrections there, coefficients, and so on. It's also important also that this model compute distance normal to the wall, like in the K Omega SST. Okay, so I'm going to show you a little bit about this correction. So you need to enable that in SVSkin, and that's it. Okay, here you have a brief explanation. Also here I have the reference paper. This is the paper used, the reference to implement this model. Very interesting, and I'm not going to discuss every single detail. I just want to show you, you have all the equations, you have a very nice discussion, how it was implemented, the reasoning from these coefficients, okay, what we can do to get these values, those values, or how to make, the model fit some specific application like aerospace applications, airfields, and so on. So what is interesting here that, okay, we have many functions, all the implementation, as I mentioned, always that validation, this plot. Okay, this is the way to know if you're doing things right. But look at that, now we have this plot here. And here you have no diffusion, distraction, but you have production. And look at that, production is very different from the other two equations model. Remember that we talk about the production of that transport equation in the two equations, the TKA, the torque kinetic energy. Here will be the production of nu tilde. And we mentioned that it's something about in the buffer layer 10 to 20. Here is not the case. So there is a difference. We need to get also that specific production term. So if we look at the original equations, our production term, it is this one, okay? So it's almost exact 4, but the behavior now is very different. So this is the importance of knowing what is happening. Like this, in this object, all the quantities that take place in your transport equation will have slightly different behaviors, okay, but similar observations that we have done so far. You will see those observations, production, destructions, and so on. Then, okay, the model, it comes in different forms, okay, as I mentioned, many corrections. You have near wall, okay, then you have wall functions, treatment, and so on. So very interesting. You can go here and read that. Then there is another paper. So in the video description, I will put the names as references. So these are many clarifications of the implementation, what has been done. So pretty much also, I think you find in this link here, you will have that. Very interesting also. And a little bit to mention that there is many people say that one equation models are incomplete models, they are not right. So this is a nice paper also by Philip Spalart. And well, he mentioned something here about this closer with one equation. And usually we have the conception of when deriving models or working with turbulence that two equations are complete models in the sense that from those two variables, you can get integral length scales, you can get turbulent viscosity, solely based in dimensional analysis now, and some other quantities. Instead, that is not possible in theory with one equation models. However, these models, they has been implemented, calibrated in such a way that we can say they are complete. So here just highlight something about those comments now. And then another paper is saying concept now that this SA model has been extended now, has exceeded expectations, and is very useful for a large range of application. In particular, it works very well with flow separation and so on, okay? So don't get fooled that because it is one equation, it's not a complete model, people call it incomplete or it's not robust, it's very robust, okay? And okay, so yeah, so a little bit here, I don't want to go too much into detail. I have some other references. This is to talk about wall functions and so on, but that will be another video. I don't want to extend this one too much. So at this point, let's get, okay, by the way, also, I always have my slides here, so pretty much will be the same, just revisit a little bit here. So pretty much what we saw, so you have a summary here. So as the other model is based in the business hypothesis, the linear eddy viscosity. Important, this model, there is no transport equation for K, so K is not computed. Okay, so later we're going to see some details in the implementation, but there are some implementations that K is computed, in an algebraic fashion. This model also, it is the foundation for these models. Okay, later we're going to talk about that. Here you have the references. There are many variations I mentioned about this model. So you have correction for rotation, curvature, trig terms, production limiters, and so on. Okay, so as I mentioned, this model has been modified a lot. So pretty much what I say that we have the busyness hypothesis. In the busyness hypothesis, we add this extra term. There is some logic behind. So in the repository of the slides, you will find one set of slides that will explain how it's get and why do we get this term. But as in this model, we don't compute K, this disappear. Okay, so it can be seen as a drawback, but in the implementation that has been corrected by adding some other functions, coefficients, and so on. As I mentioned, it's our artificial method. So we look at the equation like this, and then we start to construct a new equation. So basically that new equation to compute the turbulent viscosity is the nu tilde, it's a modified tilde, and this is the transport equation. Okay, so we have production, destruction, and then the transport, and an extra term here. That we can see as a source term. At the end of the day, you compute the turbulent viscosity like this. So we have this damping function that will take this behavior, okay, and then we go here, we have the vorticity tensor, strain rate tensor, and so on. So many functions. So as you see, there is a lot of mathematics here, okay, and when implementing this, Philippe Spalart and Allmaras, they look at a lot of data and try to get the best fit of these functions to reproduce on observations. Then our closure coefficients, okay, which can be modified, okay, it's up to you, but advice always take, but it's recommended by the authors. And here the boundary conditions. So basically quite easy. So 0 and 0, and then enable those wall functions, and then far field. So then also, if information related to torque energy and turbulent dissipation is available when setting this one, you can get the free stream condition for nud and nu tilde like this, if you have that information available. Okay, so sometimes you can have it, so probably this will be a better approximation, but at the end of the day, remember, you need to get something that it makes sense, not far from reality. Okay, so that's all for the theory, and at this point, let's move, okay, to the case. So as you go to the cases, to the directory, here you have the SA, Spalart-Allmaras. As usual, we have high re, low re implementation, and let's enter and let's visit high re, and then we move to low re. Okay, so I'm going to, here I already have the solution, okay, but I'm going to rerun just to see what is happening on the screen. So when it comes to the constant folder, nothing changed. The only thing that changed is the choice of the turbulence model. So there you will see this Spalart-Allmaras. Then we have 0 origin. So now we have the new variable nu tilde and nud, okay? So let me open these two. So nud, okay, here usually nud recommended. You have the slides here, so just to go back here, so nud, okay, you can take this value 0 at the wall, but at the far field also you can take something 3 to 5. I like to use 1 to 10 in this case, and taking nud equal to the molecular viscosity. Then when it comes to the walls, you use wall functions, okay? And here you enable the y plus basic. So in the next video, we're going to clarify what is this. Then you have this one, and so on. Then you have also the one based in the torque kinetic energy. It will work, but the results are going to be the wrong ones, okay? So you can put it there, and then at the end of the day, you are going to see that you're going to get the wrong results. So it's up to you. Personally speaking, when it comes to high ray wall functions, I like to use this one. These two are they work better when you have wall resolving meshes. So this one, well, you have it in the name, low res. So as you put it here, you're not going to get good results. This one, it is a general one, probably is the best choice. I put the comment there. But in this case, you're going to get results that they are correct, but they might be better. Doesn't say that it's wrong. Probably you need to improve numerics, iterate a little bit more. But as I mentioned, when it comes to high res, go for this approach, is better. Then nu tilde is straightforward, just fixed value 0. Okay, so in this case, I'm choosing nu tilde 10 times the molecular viscosity, then 0 gradient, 0 gradient, 0 gradient, and at the wall fixed value 0. That's all. So as you see, very easy to set up boundary conditions. Now we go to the numerics. Okay, so when it comes to the numerics, pretty much it is the same. We know well these files, I hope, no, at this point. So Control did. I like always know, in this case on this series of videos, I'm saving always know this term. So here we have, be careful that this G is not the production term, okay? So it should be G capital, no, but in this case the production is this one, Spalart-Allmaras S tilde, Okay, this will be the dissipation one, and this is the distance normal to the wall, no, a square distance, so you can plot that one. And to stress something about this S tilde, let me go to the original source, let's say this one. So it's this one that we're going to plot. Okay, so we have S tilde, no tilde. Then these values are not adding in the cache term, but these values are also safe. Okay, but I will get the basic one, and that's it. Okay, the rest is pretty much the same when it comes to SV solution, nothing new. Okay, pretty much the same. Then SV schemes. Okay, now we're solving for nu tilde. So I put there for all variables, but this is only for nu tilde that you have it here. And then remember, this is related to the way how the distance normal to the wall is computed. Okay, so here you have an extra entry there that you can save normal distance and so on. Just to show you something, for instance, we're interested in this keyword, and let me go here and let me open, okay, and go to your source code. And I always, when I see new entries, I like to interrogate my installation. So look for this keyword, and this is going to tell you where do you have it. And clearly here you can see that momentum transport, we know that this is where you have the turbulence models, and you have all models where this keyword appears. This is telling you these models, they compute the distance normal to the wall. So you can see that you have the K epsilon line breadth needs that value, the lean qubit needs that value, the lean Lechner needs that value, KKL omega, which is a transitional one, needs that value. All the K omega SST needs that value, so it will be SST, SAS, and the transitional one. Same way, the DES models based in the K omega SST will require that value. And curiously, I didn't know this one, that the Reynolds stress require that value. I have to check that one, but at least it is there, or this one, the LRR requires that value. And then you have the Spalart-Allmaras. Okay, then also, if you want to know a little bit more this method, because you have different methods, so you have the mesh wave, you can proceed in the same way. Let me go grep -r, paste there, and look at that. This is the location where you have these implementations. So you have the mesh wave, and usually you open the point H, is where you have some comments. So let me go here, more, paste, and there you go. You have the comment. There is no specific reference. However, probably you can check another method. So look at that, you have two methods. So mesh wave, Poisson that I already mentioned, and this is the one that I always forget, the advection diffusion method. So as usual, you can open here the H, and here you have some references, and there you go, some explanations how to implement it. So as I mentioned, these methods is to compute the distance normal to the wall. Honestly, go for the mesh wave method. It's the one that works the best. In some cases, it's not going to work, so you can switch to the Poisson or to advection diffusion. Poisson method is also very good. However, you need to have good quality meshes. So the quality of the mesh is not so good. Avoid this one. This one, honestly, I have not much experience, or I have tested. It tends to be a little bit more expensive, and I get a strange result for some very specific cases. But in theory, all of them will compute that distance normal to the walls. Okay, so I hope that is clear to you. Okay, what is the meaning of that? And I always invite, when you see new keywords, just interrogate the source code. So I rely in these shell commands and so on. So at this point, okay, let's run the high-res. So to be clear here, and high-res, we're going to run nu tilde. Okay, let me open this one here to reopen, using the nu, the one I recommend for high-res. Then we have a few cases, few solutions there. We're going to take a look at that. But let me launch this one, okay? So, and there you go. So now that it's running, and while we wait the solution, let me show you here that I already have, you should have these figures there. And look at that, I have the usual post-processing, but I would like to show you F3, that we have the friction coefficient there. We have different solutions here, and the one that we're running is this one, Y plus base, okay? So the y plus base, we get this result, okay? So we're using the wall function. Look at that, everything looks super cool, no problem. And now let me open this one, Spalart. Okay, so we have this Spalart here, and if we compare, looks very similar, but there is a small difference here. So look at what is happening. It's getting the behavior, but then here has this behavior that seems to be strange. This doesn't mean that the solution is wrong and actually the behavior, okay, the trend is correct, but there is something here. This doesn't mean that it's wrong implementation or it's divergent. It might be the case that you need to iterate a little bit more. I don't know. Remember, all these cases are fixed to 2,000 iterations with some numericals. So at this point, I invite you to test and try different on the relaxation, probably iterate a little bit more to see if you can get a better matching. But this is what I say, that the Spalart wall function is better for the wall resolving meshes, for wall modeling. The one based in velocity, the U one, it tends to give better results. Then in the next video, we're going to check the other combinations and we're going to see the behaviors, okay? But at this point, look at that, we have a solution, okay? And when the case was running, everything looks okay. So no tilde, nothing strange, your quantities, your y plus, okay? So you have your values there. And at this point, let's do the traditional post-processing. So we have the 3 states in Paraphone, and let's look at all of them. So Paraview is state 1, okay. And there you go. So we have a state 1, and here let me update this one. Okay, so I have a new quantity, so let me switch it off. What was that quantity? Okay, this one I don't need it. And there you go. Okay, so let me save it as well. So as you see, in nothing is strange. It is correct solution. Here you have your budget. So also let me, the shear stress budget. Let me switch off that extra quantity there that I don't want it. And let me save state. Okay. And everything will make sense here. As usual, remember that I don't recall if I always update the shear stress. So always go here and spreadsheet and look at your shear stress. So this is here, and in the calculator, let's see that, okay, so it needs to be updated to the right value, apply, and you see that a small change. And so see that small differences can have a large impact here, in particular in the buffer layer, the most energetic one. So, but still results, they are correct. And let me move here. And if we look here, we have node, and as we mentioned that it tends to peak, in the boundary layer, the maximum value of node. So we have that behavior here. Okay, we can observe that, but also we can take a look at nu tilde. Okay, so our nu tilde also, it peaks somewhere there. And well, we have the shear laminar, shear turbulent, that should be all there, and all the other quantities. So this will correspond to the dissipation there. So see that in the buffer layer, it is dissipating the most, just to avoid the turbulence scales to enter into the viscous layer. Then production there, so everything produced there. Then we have G, this is a constant, so recall that in the turbulence model. So just to make, so that is not the production, G is a function, and let's see if I have it here, is this G. Okay, you have that function there, and so on. So, and this is the distance normal to the wall. Okay, so let me go here. Remember that that is a square distance. So for instance, if I go here, let me put from 0 to 0.01. Okay, and here it should be, okay, 0.1, but that is a square. So this line there, okay, we have it at 0.1. Okay, so now let me apply a calculator, another calculator here, just to show you and to place a results. Let me take this quantity and let me take the square root. So you get y wall. apply, and let's put here 0.1, and there you go. So there 0.1. Okay, so here you can see that actually now from 0 to 0.1, that is the distance normal to the wall. I have it there. Okay, so that's it for this plot. Okay, we're happy there. So now let's open the other plot, that is the interesting one where we have the production term. Load the state here, open, and here we go back to the paper. So basically this is the behavior that we're going to see. Where is it? This one here. So production, look at that, we have it like this. So see that production now is active at the wall. In the two equations, it's not active at the wall. You start to produce in the buffer layer, which is the energetic region now that we mentioned. And here it is. So we have nu tilde that they have the same behavior, small differences for this case. Okay, they behave similarly. And here we have all the budget of shear stresses plus the extra terms. So the one that is production is the green one. Okay, and look at that. As for the paper here, it's following that behavior, but we're not resolving down to the wall. But see that is increasing as you get closer there. Then we have our contribution nu tilde there. Then we have the dissipation one, this one CV2, which is the orange one, and it is in Q2 in quantity of interest 2 in this axis. So let me, okay, so there you go. Its behavior probably I think it's a little bit different, so it will be this one. So yeah, it's increasing. So yeah, it follows that behavior there. Okay, and this is it. So from here, another, okay, by knowing the theory behind, we can say that what we have done, it is correct. And the final plot that we're going to look at, it is the state tree, the one where we have the shear stresses, the friction coefficient, sorry. So everything is okay. And there you go. So this is it, nothing to complain here. Okay, very good match with the correlation, but also with the other reference result from another CFD software. So recall here that we might need to update this. So let me go that probe, the shear stresses. Already, I think I already have it in memory. Okay, so we put it here, and this one will only affect this plot. Okay. There you go. And state tree, so we have everything updated, and there you go. So this is how we set the Spalart-Allmaras high rate. Okay, so we validated. Important takeaway is that for high rate, I recommend you to go for this one. This one you can run in next video. We're going to see differences and so what is happening, but the results are wrong. You can even disable everything. So you disable everything, taking that DNS approach and so on, but the results are not going to be correct just because of the mesh and so on. So let me close here. We're done with this case, and now let's move to the low rate. So in the low rate, I'm not going to run, I already have the solution there, and let me just launch Anaconda just to show you in this case, Python plot washer log. So we have the log file, and look at that, perfect solution. Okay, nothing strange, the quantities remain bounded. Then here you have your Y plot, so wall resolving, no problems. Okay. Then let's do the post-processing, but before doing the post-processing, let me go here, move, load rate, and to stress something about this too. So nu tilde, nothing to do there. Okay, it's pretty much the same. Okay, nu tilde, put it here. Okay, so see, this will be pretty much the same definition, independent of the fact that if it is wall modeling or wall resolving. Nut here now, look at that. We have I'm using the nut U Spalding, but you can also use the nut load re wall function, okay, or the node u. All of these are going to work. This one is going to run the simulation. Actually, I think the actual implementation, it should crash immediately because you don't have that quantity, but it runs. I recall that in older version it crashed. Now it's run, but the results are going to be run, and you can entirely, completely disable that wall function, but the results also are going to be run. So this is it, okay? Wall resolving, you can go for any of this one. Personally speaking, wall resolving, no, my best choice would be not Spalart. So in the next video, we're going to see a little bit some equations, what is happening there. But let's focus here just to the validation, post-processing, case setup. By the way, also the numerics remains exactly the same, nothing changed, okay? So your control did, SB skins, everything exactly the same, okay? The same method. Also, you can play here to put different methods, try different methods, okay? Nothing will change. And there you go. Okay, so this one, let me see why. Okay. Go there. So let's open a state one. Okay, so the first validation there. Okay. And there you go. So now it's wall resolving. Your budget of shear stresses, everything makes sense, nothing is strange. Look at here, we can zoom in and we have here the function. Now the black one is our solution, then doing the blending, buffer layer, and then resolving the viscous layer. There you have it. Okay, so probably also check the wall shear stress. I don't recall if I updated, but at this point should be straightforward to do that. Okay, so this result is perfect. Now let's take the other state. Load state, let me go here, state 2, open, and this one we're going to find the production term. So we have here nu tilde, and then here our budget shear stresses plus the production destruction. Now, so look at that here, our production, the black line, is following this theoretical result here, okay? And then you have the destruction also that kind of following the same behavior here. You have the red line will be destruction. So red line will be this one here. So probably also the behavior will be a little bit different because also we're missing, no, I'm just plotting in the destruction, this function I'm missing. Also probably there are some other blending functions that they are not included in that cache. I need to check, but I'm sure for the production term I'm missing also some other terms, so it might not be it might not follow exactly now that behavior that you see here, like here, but it's just because you're missing all those functions. And just to remind you that basically I'm plotting, but I'm not adding these coefficients. Then the destruction, I have this, but I don't, maybe I'm missing some, it's missing some terms there that you will need to add posteriori, or you get in the cache memory, you know, and see where you have those terms, so you can do you can get the actual term. So this is it, okay? This is perfect, okay? Nothing to comment here. Then we have nude here, the y plus, just to show also here. Let me in the other one probably. Then let's go to the last plot, the one that we have the friction coefficient. And there you go. Okay, so perfect result. Nothing, this is already know. This is velocity profile. Nothing to add here. Okay, just that we validate our solution. Here, what I wanted to show. Let's see. Okay, we have this wall, and let's take a look at nude. So by definition, it is 0. Nu tilde also by definition is 0, so recall boundary conditions. And we can look at here y plus, and here we have our evolution of y plus. And what I would like to point out that y plus, it is not uniform. It's impossible to be uniform because the shear stress is changed now with space dimensions. So always know they change, and to go back to the log file, look at the average value, but then when you plot at the walls, also be sure that you don't have the high values or the values that might give you problems in critical regions. Okay, so in this case, probably you have high values of y plus here in the edge, but it still is well resolving. It's not a problem. But if you run a simulation and you get, I don't know, a value that you have, let's say, a well resolving mesh, and then you get a maximum value of 100 that you know is outside that well resolving idea, and you get it here in the leading edge, that is a critical region. So better you should check what is happening. But if you get that peak in something here far, that is not a problem. Okay, so use some common sense. Or always plot your y plus in the walls and check where you have those critical regions, if there are critical regions. So in this case, nothing critical. So yeah, that's all. At this point, we're done with the Spalart-Allmaras. So here, what I can say is another one bites the dust. Okay, we covered this. We're not completely done with the Spalart-Allmaras. In the next video, we're going to look at the different combinations, boundary condition, how things can go wrong, and so on, and a little bit what is this Spalding condition and the y plus, y star. But for the time, we're done. So hopefully now you know how to properly set up this case. Be careful with the high rate that I recommend to use the U-based wall function instead for the low rate. You can use any of the variants. Personally speaking, the Spalding one will give the best results. So at this point, this is all. Thank you for your attention and see you in the next video. Bye.